Okay, thank you very much for the invitation. I would like to thank the organizers for this wonderful workshop. And for those who don't know me, my name is Sasha. And today I will be talking about quantum group symmetries, both on the lattice and in the continuum. So why do we study quantum groups? We think about them in the following way. So over the last few years, we have learned that generalized symmetries have proven being extremely useful in quantum field theory, providing some non-perturbative constraints. And we treat the quantum group as a global symmetry, a new unusual symmetry, and study which constraints it can impose on quantum field theory. So what is a quantum group? It is easier to explain on example. The simplest example is denoted UQ at SL2, and it can be understood as a deformation of the standard SL2 algebra by some parameter Q. Q is a complex number. And you can see that the commutation relations of the standard SU2 are deformed, and Q appears in the commutation relations. Here, one can think about E, F, and H generators as some sigma matrices, Pauli matrices, sigma plus, sigma minus, and sigma z. When Q goes to 1, one recovers the standard SL2 commutation relations. Now, the finite dimensional irreducible representations of this algebra for generic Q are labeled by half integer spin L and are 2L plus 1 dimensional. So it is very similar to the standard SL2 case. However, what actually differs from the SL2 is the action on the tensor product of representations, which is given by the coproduct. And you can see that for the standard SL2, the coproduct would look like E times 1 plus 1 times E. And instead here, it is Q deformed. There's this factors Q to the H, Q to the minus H appearing in the coproduct. So we have a very particular example where the symmetry is realized. This example is a spin chain with a Hamiltonian given here. As you can see, this is an open spin chain Hamiltonian because the sum goes from 1 to L minus 1. And the bulk part of the Hamiltonian is just the standard XXZ Hamiltonian, but the parameterization of the coupling in front of sigma z is given in terms of Q. But what is important is the boundary term. This boundary term provides us the quantum group symmetry. There is also a version, a closed version of the spin chain, but the boundary conditions will be more sophisticated. And on the lattice, we can explicitly write the quantum group generators using the coproduct many times. The generator Q to the H is very simple, but E and F, because of this non-trivial coproduct, they get this string of Q to the sigma z or Q to the minus sigma z attached to them. And schematically, we can draw these generators with this green line of Q to the H or Q to the minus H attached to it. And one can explicitly check that this Hamiltonian commutes with all the generators, commutes with the quantum group. And there are two immediate consequences from this. The first is that this string of Q to the H is now topological, and one can freely move it around. And the second is that the spectrum of the Hamiltonian is 2L plus 1 degenerate. Let us now focus on the closed spin chain. As I said before, Q is a complex number, but there are two most interesting regimes of this spin chain when Q is real and when Q is on the unit circle. When Q is real, the theory is unitary, and the symmetry group becomes the real form UQ of SU2. So in principle, such a symmetry can exist in the unitary theory as well. But we are studying a Q on the unit circle with this parameterization. In this case, the theory becomes PT symmetric. But the reason why we study this Q is because we have a better analytic control of what happens in the infrared. In the IR, the spin chain flows to a CFT with a central charge less than 1, given by this parameterization. It's very similar to the minimal model parameterization of central charges, but now mu is a real number. It's not an integer. And we know the spectrum of the CFT it is given by the H R, comma, 2L plus 1 H R1. These H's are the standard conformal dimensions from the class table. And the spectrum is also 2L plus 1 degenerate. It's the same L. So for generic mu, most operators will have non-integer spin. So we will have to work with the defect-ending operators. We will schematically draw them in blue like this. So now we are on the considering closed boundary conditions. So the theory lives on a cylinder, and we interpret the closed boundary conditions as this orange defect here, and the green defects which appear in the generator C and F will end on this orange defect. So such generators will act on states of our theory. But now we would like to consider how this quantum group acts on the operators. Usually we act on the operators with a commutator. Instead, for these Q-deformed symmetries, the action is also being Q-deformed. It is called Q-adjoint action. Sometimes it is also called Q-commutator. And indeed, you can see that the adjoint action of E and F is the commutators which are being slightly modified by this Q to the H. The adjoint action of Q to the H instead is very simple, just a conjugation, because this Q to the H is a U1 subgroup of this symmetry. So if we now put all these ingredients together, we have the blue operators, defect-ending operators from our theory. We want to act on it with a quantum group generator. We surround it by a closed contour. And then we deform this contour to get to the Lorentzian picture. And if one carefully does it, one gets exactly this formula for the adjoint action of the symmetry. And importantly, this action also reproduces the correct quantum group coproduct. What I mean by this is one has to act on two operators inside this contour, and one would get a correct quantum group coproduct. So now we have defined the symmetry, and what are the consequences of this symmetry on a quantum field theory? I will sketch them without the derivation. So as I already mentioned, the symmetry charges are now non-local, and the local operators have to be replaced with the operators attached to topological lines. Then the constraints on correlation functions of such operators are as powerful as the constraints coming from the usual symmetries, say SU2. And these constraints can be written in terms of quantum group coordinate entities. Another constraint is that the permutation of these defect-ending operators has now to satisfy braid locality condition, which means they have a non-abelian anionic behavior. And the correlation functions manifestly satisfy crossing with the quantum group CJ singles as a crossing curve. And imposing all these consequences on our theory, all these constraints, we were able to solve the IRCFT, find all the 2-point and 3-point functions. And also, interestingly, when Q is a root of unity, we have unitary subsectors of local operators. If somebody is not satisfied with the continuum description, we also do some numerics. We consider the operators in the spin 1 multiplet. There are 3 of them, B plus, B0, and B minus. We have explicit formulas for these operators on the lattice. We do the DMRG to measure the 2-point function of V0 as a distance I minus J on the lattice. And in the log-log plot, we get a nice straight line. And from this straight line, we can extract the conformal dimension of the operators. So we repeat this procedure for several different values of Q. Q is parameterized in terms of mu you can see on this plot. And we get a relatively good matching of our measurements with the analytic predictions given by these solid lines. And the last point which I want to make is that in the literature so far, the quantum groups have been discussed mostly in terms of, in the context of integrability. And this is how they were discovered. However, how we formulated the quantum groups, it's purely in terms of, it's like a global symmetry. So what we want to do, we study the deformation of our Hamiltonian, which breaks integrability. This deformation typically is a next to nearest deformation, next to nearest interaction term from the lattice. So we were able to construct such a deformation. And then to show the breaking of integrability, we studied the level spacing distribution. When there is no such deformation, lambda is 0, we get that the level spacing distribution is well described by Poisson statistics. And for some non-zero value of lambda, we get a nice description in terms of linear curve. So to sum up, quantum group symmetry exists both on the lattice and in the continuum. It provides constraints on QFT operators and correlation functions, and it provides novel properties for topological lines. And more generally, I would like to conclude that the theory of non-local charges is a promising and underdeveloped branch of generalized symmetries. So thank you for your attention.
Maybe on slide 4, you showed something about the asymmetric sample chart.
Yes.
This is not the minimal model, is it? Or...
No, it's not a minimal model. We have infinitely many operators.
But is it the analytic continuation of a minimal model in the problem and the non-integer values?
It's a bit bigger than that. So, for example, there is a generalized minimal model, which is an analytic continuation, for example, for the HDS minimal model. So, but this generalized minimal model doesn't have these 12 plus 1 degeneracies. So we even extend it and we add these degeneracies.
But it's a non-unitary model.
It's a non-unitary model. Yes.
When you do the breakdown analysis of the level statistics, we will get with the vacuum distribution, we will look for a single result.
Yeah, exactly. Exactly. We resolve the symmetry. So this statistics is in the sector with L equal 1, M equal 1 quantum numbers under this quantum group, which means that in this sector, there is no additional symmetry, which results into this behavior.
So when you look for anomalous dimension, you extracted it from correlation function, not from just energy levels. Is it the reason here the first like the usual work?
Yeah, so we can extract it both from the eigenvalues, doing exact diagonalization and studying the whole line states. But here our goal was actually to write explicitly these operators on the lattice, which are in exact spin 1 multiplet, and we wanted to measure the correlation function.
Good. If there are no more questions, let's thank Safir again.